So these are the properties of resins. Any resin you take must be insoluble in water and other organic solvent, and it must contain active counter-free ion for the exchange process to be taken place reversibly. There must not be any physical change expected. The resin must be highly cross-linked, and the resin must possess greater swelling ability, and it should be with large molecular mass. Let us going to understand about the synthetic resins, how we are going to synthesize ion exchange resins, both cation exchange resins and anion exchange resins, and strongly acidic resins and strongly basic resins, weakly acidic and weakly basic resins. How do we prepare the cation exchange and anion exchange resins? A very important process during the preparation of ion exchange resins, whatever may be either cation exchange resin or anion exchange resin, for both the types of resins, the first step will be common. First, we have to prepare a copolymer. By copolymerization process, one of the most commonly used pairs of compounds in order to prepare the copolymer are styrene and divinyl benzene. A copolymerization reaction will be initiated by mixing styrene with at least 4 to 12% of divinyl benzene in order to get a copolymeric substance of styrene and divinyl benzene. Here, the divinyl benzene is used up to 8%, and this is going to give you appropriate cross-linking for the resin. A copolymer will be having highly cross-linked structure. Why this highly cross-linked structure? These highly cross-linked structures will become more rigid and brittle. Therefore, the lifetime of those resins will become very long, and the flexibility of using those resins for the reversible applications will also be very high. And if the cross-linking is more, if the resins are highly cross-linked, the exchangeable ions present in the resin will be substantially more. So more exchangeable groups will be available if you use cation exchange resin or anion exchange resin with very high degree of cross-linking. And therefore, as a result of more number of available groups for exchange process, the ion exchange capacity will also become very high. So you do remember about this first step. Styrene will be mixed with divinyl benzene in the amount 4 to 12%. Copolymerization reaction will be initiated in order to get a copolymer. So after getting this copolymer, we can convert this compound into either cation exchange resin or into anion exchange resin. First step is very common. Styrene mixed with divinyl benzene. From 4 to 12% of divinyl benzene will be used. Usually 8% will be employed in order to obtain the required cross-linking to get a brittle and rigid resin with more number of exchangeable groups with very high ion exchange capacity. If you perform copolymerization reaction, you will be able to get a copolymer of styrene and divinyl benzene. You look at here, the organic chemical reaction takes place. This is the styrene, vinyl benzene. Styrene is also called as vinyl benzene. This is divinyl benzene, or 4-ethene vinyl benzene, styrene. 4-ethene styrene is also called as divinyl benzene. This will be taken from 4 to 12% mixed with styrene. Copolymerization reaction is performed in order to get a copolymer. Here, the number of these phenyl groups present over the copolymer is dependent upon the percentage of divinyl benzene what you have taken. Copolymerization reaction will become highly substantial because of the presence of double bonds here. So the joining of more and more benzyl rings will become highly possible in order to get a copolymer in this process. Therefore, the percentage of divinyl benzene will be ranged from 4 to 12%. So this first step is common for the preparation of cation exchange resin and anion exchange resin. For the preparation of cation exchange resin, you take a copolymer and treat with chlorosulfuric acid. ClSO3H is nothing but chlorosulfuric acid. This chlorosulfuric acid is strongly acidic, and the sulfonation is going to be taken place at the para position of this copolymer. You can see here at the para positions of the free benzene rings which are attached to CS2 groups. SO2 groups are going to be linked in the form of SO2Cl. SO2Cl, sulfonyl chloride. Sulfonyl chloride is going to be attached to these phenyl groups. So this sulfonyl chloride containing copolymer is treated with an alkali such as NaOH. SO2Cl is going to be converted into SO3H. SO3H, 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 SO3H. So this is the cation exchange resin. As the more the number of SO3H groups available in the resin, the degree of cross-linking we can say as very high. As the degree of cross-linking is very high, we can say there are more number of SO3H groups are attached to these phenyl rings. So the resin will become brittle, rigid, with very high ion exchange capacity because of the presence of more number of SO3H groups. And as a consequence of this more number of SO3H groups, there are more number of hydrogen ions are present over the surface of the resin. So this is how we can prepare a cation exchange resin. Copolymerization reaction is performed between styrene and divinyl benzene in order to get a copolymer. It is further treated with chlorosulfuric acid to get SO2Cl attached phenyl rings, and this on further treatment with sodium hydroxide, we are able to get cation exchange resin in the form of hydrogen ion. SO3 minus is going to be the polymeric species.
Sir, please switch on audio. Sir, please switch on your audio, sir.
Okay. It is switched on. Can you hear me?
Yes, sir. Now we can hear you.
Mute ಆಗಿತ್ತು.
Okay. So this is I've understood about this slide.
Yes, sir.
Yes, sir.
Okay. So preparation of cation exchange resins and anion exchange resins will be having a common first step, that is copolymerization step between styrene and divinyl benzene. Copolymerization reaction takes place to get converted to a copolymer of styrene and divinyl benzene. Here, the percentage of divinyl benzene decides the cross-link nature, exchangeable groups number, and ion exchange capacity. Most commonly, 8% of divinyl benzene will be used, and which will be giving you acceptable cross-linking and more number of exchangeable groups and appropriate ion exchange capacity for the resin. So this is the copolymerization reaction between styrene and divinyl benzene to get a copolymer. And this copolymer is treated with chlorosulfuric acid to get sulfonyl chloride substituted copolymer, SO2Cl substituted copolymer. This on further treatment with sodium hydroxide, sulfonic acid substituted copolymer is going to be obtained, and this sulfonic acid substitution takes place at the para position because this is going to be the most amenable position for the substitution reaction to be happened. Now this is in the form of cation exchange resinic form, where hydrogen ion will be the free ion after dissociation. SO3 minus will be the ion attached to the polymeric group. So this is going to be the cation exchange resin. Similarly, anion exchange resin can also be prepared. First step will be common. It is copolymerization reaction between styrene and divinyl benzene to get a copolymer, and this copolymer is treated with chloromethyloxymethane. Chloromethyloxymethane. This chloromethyloxymethane will convert this copolymer into chloromethylated copolymer. Chloromethylated copolymer. These are the four positions or para positions of this copolymer. Chloromethylation takes place. Once chloromethylation is over, the chloromethylated copolymer will be treated with trimethyl ammonium hydrochloride, or trimethylamine hydrochloride, or trimethyl ammonium hydrochloride. Upon treatment of this chloromethylated copolymer with trimethyl amine hydrochloride, you are going to get an anion exchange resin, which is in the form of chloride ion as a free species, which is available for the exchange process. So this is anion exchange resin. Similarly, the cation exchange resins can also be prepared by using methacrylic acid and glycol bis methacrylate, and the resins prepared in this way are going to be weakly acidic resins, because the carboxylic acid is going to be the functional group which will be available in order to make the free ion available for the exchange process. Methacrylic acid react with glycol bis methacrylate. 2 moles of methacrylic acid reacts with glycol bis methacrylate. This is going to be glycol OH CS2 CS2 OH, and methacrylic acid react with ethylene glycol. You will get glycol bis methacrylate. You will get a copolymer. You will get a copolymer between methacrylic acid and glycol bis methacrylate, because carboxylic acid has the tendency to undergo dissociation. As a result of dissociation, this carboxylic acid will be converted to COO minus with existing hydrogen ion as a free ion, and which is able to be exchanged by the cations which will be present in the sample solution. So this resin is going to be weakly acidic resin. Weakly acidic resin. So like this, weakly basic resins can also be used. Now, as per the preparation, the property of the resins, the definitions of cation exchange and anion exchange resins can be depicted. So cation exchange resin is a high molecular weight cross-linked polymer containing sulfonic, carboxylic or phenolic groups, because these are acidic. Sulfonic acid group means SO3H, carboxylic acid group means COOH, phenolic group means OH group. So the hydrogens of SO3H, COOH and OH group will be obtained with the positive charge, and these hydrogen ions are able to be exchanged by the positively charged species. So any cation exchange resin will be having high molecular mass, highly cross-linked polymer it will be, with the functional groups like sulfonic, carboxylic and phenolic groups in the integral part of the polymer with the equivalent number of cations, means the hydrogen ions, and they are called as free ions. Similarly, the anion exchange resin, it is a polymer of high molecular mass which will be containing an amine or quaternary ammonium group as an integral part of the polymer lattice, and an equivalent number of free anions such as chloride, hydroxide, sulfate, nitrate, bromide, etc. So these free anions will be exchanged when you pass a sample solution containing anions through the ion exchange column. So anion exchange resin is a resin in which free anions will be present as a mobile ions, and they are going to be exchanged by the anions of the sample solution. Any resin you consider, it must fulfill some fundamental requirements. What are those requirements? So as I told you, the resin must have a large degree of cross-linking, because in order to provide more number of exchangeable groups, and the resin must be hydrophilicity in order to permit the diffusion of the ions during the sample introduction. If hydrophilicity is more, then only into the porous of the resin, the penetration or the diffusion of the ionic species will become possible. The resin must have accessible ion exchange groups, then only the exchange process will be expected. If the resin with non-availability of the ion exchange groups, we cannot expect any ion exchange process. During the course of the separation by exchange equilibrium, the chemical stability must be attained with respect to the resin. If the resin is undergoing any chemical transformation, that resin is not going to be useful for the ion exchange chromatographic separation. And after swelling, the resin must be denser than water or other solvent we will be using, because the resin should occupy its own space comfortably throughout the separation in the column. And the solvent, whatever we are passing through the chromatographic column, must be freely moving, must be freely traveling, must be freely flowing by passing through the resin. So the resin must be packed tightly in the chromatographic column, which is having larger density. If it is having a lower density than the solvent what we are going to use, then it will be floating. The resin will be floating in the liquid what we are going to use as a solvent. So these are the requirements of the resin. So the ion exchange chromatographic separations can also be done by applying very high pressure by utilizing the principle of HPLC. While performing the separation by this means, the resins also have to meet some requirements. What are those requirements? Whatever the resins we are going to use for the separation of ionic solutes by HPLC instrument, by adopting the principle of ion exchange process, the resin must be a pellicular one, which must be containing microparticle packings. The column must be containing microparticle packings. So these microparticles will be having very, very small particle size, mostly from 5 to 10 nanometer, very, very less particle size. And this is going to be responsible to eliminate the multiple path transfer term in Van Dimter equation. So in order to decrease the band broadening, or in order to decrease the value of H, in order to increase the resolution, in order to increase the column efficiency, the particle size is going to play very, very important role. So some silica based packings are also be prepared by chemical process, silica, you can convert that OH groups by chemical treatment so that the silica can be made to be bonded with functional groups in such a way that it must having fixed ions to the silica polymeric surface and mobile ions which are able to be exchanged by the ions of the sample solution. So the particles which are filled into the chromatographic column must be narrowly distributed so that the column efficiency should be very high and the resolution will be very high. This can also be achieved by using the stationary phase particles of lower particle size. So these type of stationary phases or ion exchange resins will be used for the separation of amino acids, peptides, proteins, nucleotides, and other biomolecules also, because these compounds will be available in the ionic state, particularly in the Zwitter ionic state. We can increase the ionic property of those compounds, so we can initiate the interaction of ion exchange process. Therefore, they can be separated more commonly. So let us understand about the common action of ion exchange resins. Whatever it is, whether cation exchange resin or anion exchange resin, whatever it is, you consider the first reaction. What I have written here is a cation exchange resin. Resin is having a B plus free ion, movable ion. A minus is attached to the polymeric bed. This is not movable, this is fixed. B plus is going to be moved. If you pass a sample solution containing cation C plus through the chromatographic column, C plus is going to be exchanged B plus. So B plus will be traveling out of the chromatographic column. So if you pass a calcium solution through a cation exchange resin in the sodium form, calcium 2 plus ion, divalent calcium is going to be exchanged in place of sodium ion. This is going to be Ca2 plus in order to release sodium ion as a effluent. If you consider anion exchange resin in the chloride form, if you pass the sample solution containing sulfate, sulfate is a anion. So two chlorides are going to be eliminated by exchange process, by exchange process by sulfate ion in place of chloride ion. Similarly, OH minus ion in place of chloride ion, chloride ion in place of OH minus ion. If you pass hydrochloric acid solution through a column containing anion exchange resin, chloride will be replaced in place of hydroxide ion to get water as a effluent. So this is how the ion exchange resins, whether it is cation exchange resin or anion exchange resin, they are going to action. So in order to expect better functioning of cation exchange resin or anion exchange resin, pH is a very important factor. We can say it is a prime factor. There is no any stipulation for whatever the resin, whether it is cationic or anionic, pH from 1 to 14 is recommended. pH from 1 to 14 is recommended for whether cation exchange resin or anion exchange resin you are going to use for the separation process. Whereas for weakly carboxylic acid resins, because they are weakly acidic, very little action at pH less than 7. If you maintain pH less than 7, the dissociation of these weakly carboxylic acid resins will become difficult. Very less extent the dissociation can be expected. Therefore, it is appropriate to maintain the pH greater than 7 whenever you are using the resins which are in carboxylated form. In neutral pH, if you pass sodium chloride solution, there will be no action by the pH. Very little action on passing sodium chloride, because sodium chloride is a neutral solvent. This will dissociate to get converted to Na plus and Cl minus. So if your resin is positively charged species free ion contained resin, Na plus is going to be exchanged. If the resin is anion exchange resin, chloride is going to be exchanged. So for strongly acidic resins, pH 1 to 14 is recommended. Whatever the pH you can maintain, because they undergo easy ionization to get converted to SO3 minus and H plus form, or N plus Me thrice and Cl minus form. So 1 to 14 pH is recommended. In between 1 and 14, whatever the pH you can maintain. While using carboxylic acid resins, pH must be greater than 7. In neutral pH, no action on passing sodium chloride, means if you use sodium chloride, This will be functioning in order to convert hydrogen ion form resin to sodium form or OH minus ion resin to chloride form resin. So strongly basic anion exchanges such as N plus Me thrice Cl minus contain resins in both OH minus and chloride form. These resins are similar to sulfonated resins, strongly acidic resins. And these resins are also independent of pH. You can maintain whatever the pH required, you can maintain the pH. But of course, weakly basic anion exchange resins in acidic solution behaves as strongly basic resins. So, weakly basic anion exchange resins are needed to be maintained with acidic solutions. When you maintain acidic solution, these resins behaves like strongly basic resins. Say for example, dimethylamine resin you take. Dimethylamine resin you take. Nitrogen is attached to the polymeric surface. Nitrogen is substituted by dimethyl group. If you pass this by hydrochloric acid solution, protonation takes place in order to convert this dimethylamine into protonated one. This protonated functional group will possess strong basic property. Therefore, these resins will function like a strongly basic resins in the acidic medium. So, this is a weakly basic species attached to the polymeric surface of the resin. So, therefore, this can be called as weakly basic anion exchange resin. If you pass this with hydrochloric acid solution, this resin will be converted into strongly basic one. So, in order to remember to a better extent, strongly acidic and strongly basic resins are independent of pH. Whatever the pH you can maintain for the separation process to be performed. While using weakly acidic and weakly basic resins, either you have to maintain basic medium or acidic medium. If you are using weakly acidic resins, basic medium you have to maintain. If you are using weakly basic resins, acidic medium you have to maintain in order to convert the resins into the exchangeable one. Otherwise, the effective functioning cannot be expected. So this is what the effect of pH on the ionization of the resins, so that the free ions must be existed in the stationary phase in the ion exchange resin, so that the ion exchange equilibrium can be expected to the better extent. So all this ion exchange process is because of the ion exchange equilibria. Let me assume a chemical equilibrium reaction between A and B. The ion present in the resin is going to be reacted with the species or the solute present in the solution. So the species from the solution is passing through the ion exchange resin. The species present in the solution is replaced in place of this R, because this R is an ion which is having the ability to get exchanged. The species S is going to be exchanged in place of R, and S is going to be exchanged by R. R is going to be exchanged by S, S is going to be exchanged by R. So AS plus BR is going to be taken place. If you use law of mass action, the equilibrium constant for this equilibrium reaction is simply the ratio of the concentration of products to the concentration of reactants. So concentration of BR into concentration of AS divided by concentration of AR into concentration of BS. This should be AR. The equilibrium constant KAB, the equilibrium constant is denoted by KAB. This equilibrium constant is called as selectivity coefficient. So what do you mean by the importance of this selectivity coefficient? If the value of KAB is greater than 1, then we can say the resin will become more selective for the solute B. whatever the ions present in the sample solution be, the resin is going to be selective for the separation of the ions present in the sample solution if the value of Kab is greater than 1. Assume any solute present in the sample solution that can be separated with maximum efficiency if the selectivity coefficient is greater than 1. If the selectivity coefficient is less than 1, then the resin selectivity will become lesser for the separation of the solutes present in sample solution, that is solute B. It cannot be separated with maximum efficiency. Therefore, the resin selectivity will be retained for solute A only, or ion A only. So this is about the ion exchange equilibria. Ion exchange equilibrium expresses the equilibrium relationship between the exchangeable ion and ion present in the sample solution. The ability of the resin to exchange the ions present in the solution is expressed by selectivity coefficient, that is denoted by Kab. This value must be always greater than unity in order to say the resin selectivity is appreciable. You can look at this table in order to compare the performance characteristics of cation exchange resin and anion exchange resin. This is strongly acidic resin, cation exchange resin, that is sulfonic acid resin, SO3H resin, where hydrogen ion is the free ion. Hydrogen ion is a free ion. The relative selectivity coefficient, the value of Kab are presented here. If you pass lithium solution through the cation exchange resin, the selectivity coefficient value will be 1. It is not greater than 1. So the resin, the cation exchange resin, will be less selective for the elution of lithium ion. So exchange equilibrium will be impossible. It is not acceptable. For hydrogen ion, it is 1.26. It is greater than unity. Its selectivity for hydrogen ion will be very high. For sodium ion, it is 1.88. Similarly, ammonium ion, potassium, rubidium, cesium, the value of Kab is going to be increased. This means to say that the selectivity of the resin will become very high when you pass the sample solution containing Cs plus cesium ion. Cesium ion is going to be freely exchanged in place of hydrogen ion when you use cation exchange resin, which is strongly acidic in nature. Similarly, strongly basic quaternary ammonium chloride resins, if you use, chloride will be the free anion. It will be less selective for fluoride because the selectivity coefficient is only 0.09, 0.1. Similarly, for hydroxide ion, it is 0.09. So that the quaternary ammonium resins, they are less efficient for the elution of fluoride or hydroxide ions. Even for chloride, the selectivity coefficient will be 1. But if you see bromide, nitrate, iodide, and perchlorate, the selectivity coefficient is substantially increased. So bromide, nitrate, and iodide and chlorate, perchlorate, they can be separated with maximum efficiency by using strongly basic anion exchange resins. Now you are able to understand that the functioning of the exchange equilibrium is dependent upon the selectivity coefficient denoted by Kab. This value must be always greater than unity in order to say the efficient separation or elution of the solutes is going to be happen. Next, what are the factors which affect the selectivity? First one is the nature of exchanging ion, and the second one will be the nature of the resin. These are the two important factors which will affect the separation, which will affect the ion exchange equilibrium. Let me discuss about the nature of exchangeable ion. What is the ion which is going to be exchanged? If you look at here, sodium ion, calcium ion, and aluminum ion, and thorium ion, monovalent, divalent, trivalent, and tetravalent. So whenever if you wanted to separate these ions by using a cation exchange resin which is present in hydrogen ion form, the first condition is you have to use the dilute solutions of the sample containing all these ions, dilute solutions, and separation can be done under ordinary temperature. So the exchange process, the exchangeability of the resin increases with the increased charge. as the charge on the ion is increased, the exchangeability of the resin will become more. Means, if you pass the sample solution containing thorium 4 plus, aluminum 3 plus, calcium 2 plus, and sodium ion, the exchangeability of the resin for thorium ion will be more when compared to aluminum, when compared to calcium, and when compared to sodium. So thorium is going to be exchanged in place of hydrogen ion to a greater extent rather than aluminum or calcium or sodium. Okay, this is of course true whenever we consider differently charged species: monovalent, divalent, trivalent, and tetravalent. All these species are having same charge. They are all monovalent. For all these singly charged species, the exchangeability of the resin will increase with the decrease in size. So the exchangeability of the resin for lithium will be less than hydrogen ion, which will be less than sodium ion, ammonium ion, potassium ion, rubidium ion, and cesium ion. Means the exchangeability of the resin which is in the hydrogen form or which is cation exchange resin will be more for cesium ion, because this is having lesser size. Cesium ion will be having lesser size than rubidium ion, than potassium ion, than ammonium ion, than sodium ion, than H plus ion, than Li plus ions. Okay, so for singly charged species, under the similar conditions, means under the concentration at very low level, under the ordinary temperature, the exchangeability of the resin will increase with the decrease in size. Here this is having lesser size, this is having larger size than cesium, potassium than rubidium, ammonium than potassium. Therefore, the exchangeability can be written in this particular order. For doubly charged ions, all these species are doubly charged. All the conditions are fulfilled, but these compounds available in the solution must be able to undergo dissociation rapidly, and the rate of dissociation will decide the ion exchange process. So whatever the species you consider, it must undergo a dissociation more rapidly. Then all those species undergo exchange process more rapidly. You can see here, barium chloride you consider, its dissociation will be rapid. So the exchangeability for barium will be more when compared to lead, when compared to strontium, calcium, cobalt, nickel, copper, zinc, and these two are having same exchangeability than manganese, beryllium, and cadmium.